I want to put money into an account on June 1st of the previous year, and the account earns nominal interest of 3% compounded monthly. And I want to do this to pay this year's rent of $800 a month starting January 1st of the new year. How much do I put in if I only pull out money to pay for rent at the beginning of each month? And again, I don't want to put in a penny more than I need to into this account to pay for rent. So on January 1st, well, you need exactly the present value of the rent payments, which is $800 per month. A double dot, rent payments are always annuity dues. There's 12 months, and we have a per month interest rate of 0.0025, because remember, I-12 is 0.03, it's 3%. So that gives me 0.0025. Okay, so let me just plug into our formula. Just plug and chug, so there shouldn't be any issues, but just in case. So it's 1 minus my present value factor, 1 over 1 plus 0.0025. To the 12th over 1 minus my present value factor. And this is going to be equal to 9469 0.41758. This is how much I need on January 1st. Okay, but I want to invest on June 1st, and that money is going to sit in the account for 7 months. Why 7? Well, no shame in using your fingers if it's not clear. June 1st to July 1st is 1 month, so it's July 1st, August 1st, September 1st, October 1st, November 1st, December 1st, January 1st. That's 7 months. Okay, so I need to discount by 7 months. That's how much I need in the account on June 1st. So in particular, I need to discount my 9469 and roughly 42 cents by 7 months. I'm taking the present value of this amount due in 7 months. So on June 1st, I need 9469.41758 times 1.0025 to the minus 7, or if you, same thing, 1 over 1.0025 to the 7th. And this is going to be equal to 9305.35 cents. Now, this should make sense, but if it doesn't, let's maybe think about this in a slightly different way. So on January 1st, and this is not a very efficient way of doing this, but you can do it this way if you really so desire. On January 1st, so on January 1st, I need 9469.41758. Okay. But on January 1st, I'm going to have X times 1.0025 to the 7, because on June 1st, I deposit X. That accrues 7 months of interest at the per monthly interest rate, the effective monthly interest rate of 1.0025, that accrues 7 months of interest. So it's x times 1.0025. Multiply both sides by 1.0025, then minus 7, to get the same answer of 9305 and 35 cents. Okay. Right. So let's go back to the lecture notes. All right, so now I want to do a topic that, in my opinion, is a bit maybe silly and maybe isn't so useful in the grand scheme of math, in the grand scheme of finance, but this is a topic that appears in exam FM from time to time, and hence we need to go over it, whether or not I feel like it's useful or not. Okay, and so there's a formula that's sometimes used comparing an annuity due. The same formula is basically true for present value of annuity due or an annuity immediate. And there's the same formula is basically true for an annuity, the present, so of the accumulated value of an annuity due. Here I'm just stating it for an annuity immediate, but exactly the same formula. The relationship is true for the accumulated value of an annuity due and present values of an annuity due and annuity immediate. Right, so this is a formula relating the accumulated value of an annuity immediate with n plus k periods to that which has n periods and k periods. So strictly speaking, you can absolutely just use some algebra to prove this formula. What's more useful is to derive this formula using, as I like to say, theory of interest kind of way of thinking, or exam FM thinking. And let's do that. So we have a n plus k period annuity immediate. We know the accumulated value of that. Just plug into the formula. It's P SNK J. Well, let's find the accumulated value by breaking this up into two annuities and adding those together. And we've done that. Particularly, you have to do that when you have, an interest rate change or a payment change. So in particular, the N period annuity has an accumulated value of PSNJ, but that amount accumulates K periods of interest to become P1 plus J to the K SNJ. All right, well, what about the K period annuity? Well, really no subtlety there. That just accumulates to PSNKJ, just plugging and chugging into my formula. This is a K period annuity where each of the payments are P. So you add the two up, add this here to this here, you get exactly the right-hand side here. And I think in general, it's really good to kind of get used to this kind of thinking, this theory of interest, exam FM type way of thinking. Okay, so particularly this is useful when P equals 1, and there's 3 particularly useful examples of what K is that gives you useful formulas. The first one is K equals N, so just dump in K equals N, P equals 1. Well, you just get 1 plus J to the N, SNJ, SNJ. Let's plug in K equals 2N. It's P equals 1 again. So it's, obviously 2N is N plus N. And obviously 3N is N plus 2N. So there's no subtlety on the left-hand side here. Okay, so here, K is 2n, it's 1 plus j to the 2n, S2nj. So we know what S2nj is. It's 1 plus j to the n, Snj plus Snj. And last but not least, K equals n minus 2. And replacing n with n minus 2 in the left-hand side gives me 1 plus j to the n minus 2. Or rather, oh, sorry, that's fine. Got a little brain fart there. So K is 2, so it's 1 plus j to the 2. We're replacing n with n minus 2, so it's Sn minus 2j plus S2j. Well, S2j is just 1 plus j plus 1. Okay. And here again, we're doing n minus 2 plus 2 is just n. All right, so let me do examples of all this. And again, these examples are going to be a bit silly, a bit convoluted, but, you know, these appear as actuarial exam FM problems sometimes, so something to remember. So the first example is if Snj is 100 and S2nj is 300, then find j. All right, so let's do that. So let's just write things down. So S2nj is 300. And Snj is going to be 100. Okay, so let's use our formula. 300 is S2nj, and that's going to be 1 plus j so Snj is 1 plus j to the n Snj plus Snj. Well, sorry, this is 100. I don't know why I put 10 here. But anyway. Okay, so this is going to be 1 plus j to the n times 100 plus 100. All right, so just subtract 100 from both sides. Divide by 100, we get 2 is 1 plus j to the n. Okay, well, that's all fine and dandy, but we want j. We don't want 1 plus j to the n. Well, that's fine. We can solve for j very easily. Why? Well, we know a 100 is Snj. And that's going to be, dump into my original formula, 1 plus j to the n minus 1 over j. So this here is 2. The whole thing here equals 2. Okay, so this is going to be equal to 2 minus 1 over j. So we have 100 is 2 minus 1 over j. That's obviously 1 over j. So that means j is just 1 over 100, and it's a reasonable interest rate of 1%. Okay. Yeah, so these other problems are similar, and I'll give a homework like this. Okay, so let's say instead we have SNJ is still 100, but S3NJ is 700. Find J if J is positive. Okay? So we haven't really dwelled on negative interest rates that much, but so remember, certainly you can have a negative interest rate. Particularly stocks go up and down all the time, and you can model a stock going down by a negative interest rate. And we'll see why we need to specify J as positive. Otherwise you'll have a negative answer and a positive answer. You got to figure out which one you would otherwise not know which one to use. Okay, so it's the same basic strategy here. So, right, so we have SNJ is 100, S3NJ is, what do we say, 700. Okay. So I'm using my formula for SNJ. So S3NJ is going to be 1 plus J to the 2N, SNJ plus 1 plus J to the N, SNJ plus SNJ. So this is going to be equal to plug in for for 100 in all these spots here. And we get 700 is going to be 1 plus J to the 2N times 100 plus 1 plus J to the N times 100 plus 100. So this is a little trick that you use every now and then in exam FM in various incarnations. So, right, what I want to do is write this whole thing here as 1 plus J to the N squared, so that I can let X be 1 plus J to the N, so that this is really 100, to stick it in front, X squared. So again, I'm setting, I'll use yellow here. This whole thing here is going to be X. So it's 100X squared, 100X plus 100. Okay, so now we just subtract 100 from both sides, get 600 on the left-hand side. So we're solving for X here. So you get 600 is 100X squared plus 100X. So divide by 100, you get 6 is X squared plus X. So very easy. You just factor, so it's X plus 3, X minus 2. And so remember, well, so we want J to be positive. So, right, so we want 1 plus J to the N to definitely be positive. So we take the positive one. So X is going to be 2. Theoretically, if N is even, then even when we take a negative one, so maybe I should make it more clear why we're going to take, or maybe change the problem a slight bit to emphasize we're going to take X equals 2. X is going to be the positive one, but anyway. Okay, so, right, so what do we have here? We have, right, so let's say for this problem, n is odd, so that if x were negative, then that would mean j is negative. And we don't want that. Okay, so, right, so what do we have? We have 2, remember x is 1 plus j to the n. So how do we solve for j? Well, again, we do the same thing here. We have 100. We do the exact same thing we did last time. 100 is SNJ, and we plug into the formula. Maybe make the j a little smaller so I can fit this in. So this is going to be just like before, 2, because we just found it 2 here. 2 minus 1 over j. So 100 is 2 minus 1 over j. So j is going to be 1 over 100.01. So it's the same thing. J turns out to be 0.01. So on the homework, if you get, you have a problem like this, you're going to do exactly the same thing. You would set x to be 1 plus j, so you can solve a quadratic. So, yeah, so in various exam FM problems, you have to kind of do a little bit of manipulation to get the problem to a point where you use the quadratic formula. Okay, last but not least in these kinds of problems, let's do a problem where if Sn minus 2j is 40 and Snj is 50, then find j if j is going to be positive. So here, for this to make purely logical sense, I don't need to assume n is odd, but anyway. Okay, so, right, let's do this. So let's go to new page. Okay, so, right, we're given that Sn minus 2 j is 40. Snj is 50. So again, I'm going to use my formula for Snj in terms of Sn minus 2j. So it's going to be 1 plus j squared Sn minus 2j plus 1 plus j plus 1. Well, plug in, this is going to be 40, 1 plus j squared plus 1 plus j plus 1. So again, we're going to set something convenient to be x. It only makes sense to set this to be x here, 1 plus j. So then obviously we have 40 x squared plus x plus 1 equals 50. That's a 40 here, not a 46. Sorry about that. Okay, right, so just a little bit of algebra. 40x squared plus x minus 49 equals 0. So if you haven't used quadratic formula in a while, definitely get used to it for exam FM. So it's negative b plus or minus b squared. B is 1. For AC, so A is 40, C is minus 49. over 2a, 2 times 40. And so this is going to be, we just want the positive solution. So we want, this is going to be 1.09437. Remember, x is 1 plus j. So j is going to be 9437. So j is going to be 0.09437. And again, because a problem is specifying we want a positive solution for j, we're discarding the negative solution here. All right, so we want to finish up this video by doing an example similar to homework 2.1.1 in Broverman's Mathematics of Investment and Credit book. So I personally like these problems because they're fairly realistic. You know, it's, as we'll see, this problem is quite interesting. If you understand what's going on, it's fairly plug and chug. So you invest $100,000 by purchasing a 10-year annuity with level payments at the end of each year with I equals 4% effective annual interest. So this is just an annuity immediate situation. So you find a nice investment to invest these payments into, and that account earns 6% effective annual interest. Find the amount in this account after 10 years. And also let's find the equivalent effective annual interest rate for this entire investment. The entire investment being very simply, you invest now $100,000. What do you have at the end of 10 years? So, right, so you don't really need a timeline for this, I would say. I might just draw a timeline for the reinvesting of the annuity level payments. So, okay. So let's go to the whiteboard here. Okay, so first is first, we need to find the payments. So we need to find the payments that the original annuity gives us. And this is really nothing, there's really nothing to this. It's always, it's always using the present value formula. If you buy a $100,000 annuity, that means the present value is $100,000. We don't know what the payments are, but we know everything else. It's an annuity immediate, it's 10 years, and the interest rate is 4% for this annuity. So just plug and chug into your formula. 1 minus present value factor. Well, yeah, it's probably a little easier to do 1.04 to the minus 10, but it doesn't really matter. 1.04 to the 10 over your interest rate, 0.04. And this is going to be equal to 8.1109p. Okay, so, right, so all we do is take this here, divide by 8.1109, and we get P is going to be very simply 12,329 point, let's say 09. Yeah, usually I round more, but let's just round to the nearest decimal for this problem. No good reason, I guess. I have it written down that way, so. Anyway, okay, so Right, let me just go back to the problem real quickly. Okay, so what have we found now? We've found what these annuity payments are. So now what we're doing is we're putting in at the end of each year for 10 years these payments that we know into an account earning an interest rate that we know. So we just have to use the annuity formula again for the accumulated value. So I'll just draw a timeline in case it's not clear. So everything we did here is just to find what these payments are. So the account, let's say the timeline for deposits. And again, you really don't have to draw the timeline. I probably wouldn't on a quiz or exam. But just to make sure we're all on the same page here. So the timeline is very straightforward. So there's 10 years each time. So actually rounding to the nearest cent makes this a lot easier to draw on the time diagram. Otherwise, I would not be able to fit this. So anyway, right, so every deposit you make into this account is $12,329.09. We just computed that. And the last one, $329.09. We know that for this entire 10 years, or we're given that the interest rate here is 6%. All right, so all we do is plug and chug into our formula for accumulated value, 12,329.09, S10.06. That is 12,329. Let me move the camera down a bit. Sorry about that. 12,329.09 cents. 1.06 to the 10 minus 1 over 0.06. And this is going to be equal to, just plug and chug into your calculator, 162,507 and 21 cents. So that's the accumulated value. Okay, so the last bit of the problem, which in some sense is possibly the most important, if you're deciding if this is a good strategy to do, is to figure out what the equivalent effective annual interest rate for this investment is. So you invest $100,000 now. In 10 years, you get $162,507 and 21 cents. Okay, so right. So remember what that means. So for the equivalent effective annual interest rate, let's call it I here. I already used I, but that's all right. Hope this doesn't cause confusion. So remember the whole, and this is something you really can't forget, the whole idea here is that we're pretending like this $100,000 sits in a bank account earning a certain interest rate I, and it accrues 10 years of interest. And when that's all done, we have 162,507 and 21 cents. So yeah, divide by 100,000, raise both sides to the 1 over 10, subtract 1. you get I is 0.04975. So this gives us a rate of return of 4.975%, which I don't know, depending on what you're looking for in an investment, is good or bad. I don't know, but it tells you, this gives you a benchmark for this investment strategy. It kind of allows you to compare it to other investment strategies, the comparative quantity being the equivalent effective annual interest rate. Okay, so yeah, like I said, this is similar to 2.1.1. This is a little more straightforward than 2.1.1, but it's basically the same kind of problem. So hopefully this helps. I think in general, this is a very good example. Even if you're not in my class and you're still viewing this video, and it's an example I really like because, again, it's very realistic. You buy an annuity and then you reinvest it. I mean, why not? If you can buy an annuity but you find a better investment strategy, why wouldn't you reinvest your money to get a better rate of return? I mean, to get better returns. Okay, yeah, so the next video will be on using the calculator to do annuity calculations. And actually, this problem is fairly fast using the calculator if you know what you're doing. And I suggest you try to do this problem, check using the time value of money keys, do this problem. It speeds it up quite a bit. But as this problem suggests, there's no substitute for understanding the problem. You literally just cannot plug and chug into one single formula on your calculator to get your answer. And yeah, time value of money keys are discussed in the next video. Hello, everyone. What I want to do to finish up this video is do an example similar to 2.1.17 in Broverman's Mathematics of Investment and Credit. So this actually is a little more simple than this problem, but it's similar. And this problem in the book is a former exam FM problem, so this concept is very important. And this is similar to the annuity immediate problems where we had multiple different deposits. The only difference here is that we're finding present value. Okay, so right, we want to find the price of an annuity immediate at 7%, pays $30 for the first 20 years, 50 for the next 20 years, and 60 for the last 20 years. So let me draw a timeline for the whole thing. Make sure, sorry about that. Just to make sure we're all on the same page here, that there's no confusion on what's going on. So at the end of the 20th year, that's the last $30 payment. It's an annuity immediate, so payments are at the end of the years, at the end of each year. So starting at t equals 21 all the way up to the end of the 40th year is $50. And then last but not least, sorry about that. So, right, so starting at t equals 41, going up to 60, we have $60. So just like we have payments of $60. So like before, we're going to break my annuity up into these three annuities. And I probably should be consistent and put dots here. Not that it matters, but anyway. Okay, so let's do the easy one, $30 here. Maybe I should put the dots right here, actually. Not that it really matters, but maybe makes more sense. Anyway, okay, so, right, this time diagram is pretty straightforward. This is just a plain annuity present value formula. Not much here. 30, it's an annuity immediate, so there's no double dot. Interest we're given is 7%, and that is 317.82. So I don't really need to round further because I'm just adding up these numbers. Okay, so let's get to the next annuity. So we're going to do the $50. Okay, so they start, remember, at the end at 41. So 50 all the way up to sorry. This starts at 20, or 21 rather, t equals 21, and it goes all the way up to t equals 40. So when t equals 20, at the end of the 20th year, well, this is straightforward. The present value of this annuity here, because this annuity does start at the end of the 20th year, so this is just 50 A20, like before, 0.07. Okay, but we want it at t equals 0. So we have to discount this by 20 years, whatever this is. You have to discount it by 20 years because we don't want its value at the end of the 20th year. We want its value at t equals 0. Let me try and squeeze this in. Should not be a problem. There we go. Right, and we just basically do the same thing for, well, first of all, this is going to be 136.88 cents. And it shouldn't be surprising that this is considerably less than the present value of the $30 annuity, even though this is a $50 annuity, because we're asking for the value 20 years prior to when this annuity starts. So we're discounting it by 20 years, and hence whatever this is, it loses a lot of its value discounting at 7% effective interest, not nominal, effective annual interest rate. Okay, right, so let's just do the last one. And it's basically the same idea. Here is t equals 40, and at the end of the 41st year is when the $60 start, and they end at the end of the 60th year. So again, it's a pretty straightforward problem if you understand what's going on. But yeah, I'm just doing this to make sure everyone's on the same page here. This is a very important idea to, to be able to do annuity problems like this. Okay, so, all right, give myself a little bit more room. So, right, so this is 0. So, right, whatever this is. And if you are going to do a time diagram on the exam or quiz or whatever, I would probably just actually compute this, but I just want to leave it for now. Just emphasize whatever this is, we're discounting it. And yeah, here we need to discount it by 40 years. Because again, this annuity starts at the end of the 40th year. We don't want the price at the end of the 40th year. We want the value of this at the beginning, which is 40 years prior. So it loses a lot of its value, and it becomes actually $42.45. So the price is just the present value of all three of these. So it's $317.82 plus $136.88, $42.45, and finally that becomes $497.15. So hopefully this problem was helpful. Yeah, so so long, take care, stay safe, and more videos to come soon. Bye-bye.